cannot get proper accuracy. Similarly, observer matters in the accuracy. If let's say this is a needle and this is a scale, and we first look on it from the top and then from the side, so from the side we can see that the needle can be here. So this type of error should not be made. Similarly, the variation in the signal can also occur. So let's say if in temperature change, this length become 1.1 if we measure. So just like the wires between two poles, with respect to temperature or heat that goes into these wires, the length changes. So variation in temperature can also occur. Similarly, the instruments can have some problems. So let's say we are having a thermometer that is used for checking the temperature of human body, and we use it for calculating the temperature, checking the temperature of, let's say, a heat engine. So that would also gives us some error, and it will lead us to a bad accuracy. So this is it for the accuracy. Now moving on to the precision. A precise is measured quantity which is closer to its own type of quantity. So measured quantity is checked with respect to other measured quantities. So if we have, let's say, an example of, let's say, darts. So let's say we want to hit this bull's eye. So if someone hits this point, what will we say? That it is more accurate. But if another guy comes and he hits this one first time and this one second time and this one for the third time, so we will say that this guy's values were precise. So degree to which the successive measurement difference from one another. So this is accuracy and this is precision. Similarly, if we have three values over here, so we will say that these are both precise and accurate. Okay, this is just for understanding. Now coming towards the resolution. A resolution is actually the magnification of some instrument. It is just like the megapixels of our camera. The more megapixels, the better resolution. So we can zoom in more and more. So this will probably clear your all thoughts about the resolution. That the dead zone is farther if we have a bigger resolution scale. So we can say that, let's say, these are our divisions and a quantity is here. So this is, let's say, not that much obvious that whether it is on the, let's say it is here, that it is on this 2 line or 3 2 line. But if we have more scales in it, we can clearly then say that it is on this between 1 and 2 and this, let's say, A and B. So now this thing is obvious. So more resolution will lead us to a better understanding of a point. So if we have this scale and this is 1 volt and this is 2 volt and some quantities here, we cannot say that it is 1.5 or 1.6. But if we grade it more, then we can clearly say that it is either 5 or 1.5 or 1.6. But if we more grade it, then we can exactly say that it is 1. Let's say 5. So this gives us an idea of the resolution. Now speed of response. Speed of response is actually the quickness of an instrument to read, to calculate. So you might have seen that if we use a thermal gun or a temperature gun which uses laser for calculating the temperature, so this directly gives us the temperature. But if we use a thermometer instead, so it will go from room temperature to that reading, and it will slowly gives us this reading. So this is actually explaining this phenomena, that the speed of response can differ from instrument to instrument. Now let's solve a problem on the resolution. So resolution is calculated for this particular problem. A moving coil ammeter has a uniform scale of 50 division, so it has 50 divisions, and full scale can calculate 5 ampere current, so 0 to 5 ampere. So 50 division would give us a 5 ampere current. Now this thing is not V, this is 1/4 of a scale. The instrument can read up to 1/4 of a 1 scale. So we are having further 4 scales inside this, further 3 scales inside this 1 division. Determine the resolution of this instrument in ammeter. So we want to find that what will this single step tell us about the amperes. So total 5 ampere is 50 division. So this is division. 1 division is 5 by 50, which is 1/10, which is 0.1. And now we are saying that this 1 division can further be divided into 4. So divided by 4 would give us 0.025. So 0.025 ampere is the minimum quantity that we can measure with. Now converted this to milliampere, so milliampere would give us 25, because 1 shift, 2 shift and 3 shifts, so 10 power minus 3 is this milliampere. So 25 milliampere is the resolution of this particular device. Error measurement is done for every instrument, and almost it is impossible to get the absolute true value. So there are 3 types of error measurement. The first one is the absolute error. Absolute error is the difference between the actual and the measured quantity. So let's say in the previous case we had 1.1 meter calculated as measured, and the actual was 1 meter. So the error was measured minus real, which is 0.1. Similarly, we can also have negative error as well. So do not worry if an error comes to be negative. Relative error is dividing the same absolute error divided by the true value. So absolute divided by true would give us the relative error. And if you want to calculate the percentage of this error, then we will multiply this value by 100. So this will give us the percentage of this value. Okay, so this is the percentage error. Percentage error is always relative. So this is relative percentage error. Limiting error is another thing. Sometimes the instrument are given with a plus minus values, that it can measure up to this much error. So there is one thing that is important in this limiting error discussion, is that limiting error always gives least error at full scale. So let's say if an instrument is measuring 1 volt, so 0 to 1 volt, and we say that this instrument has an error of plus minus 1 volt. So this plus minus 1 volt would be present in this value. If it is, let's say, 0.25, and if it is 0.75, and if it is 0.5, and it is 1, this 0.01 value would be present for all these values. So if we say the measured value is 0.025, so this limiting error would make it 0.25 plus 1 and minus 1, so this would be 0.26, 0.24. Now 0.24 and 0.25 is is having a bigger difference than that of if we say our reading is 1. So for 1 we can have 1.01 or 0.99. So 0.99 with respect to 1 is 0.01, but this is a very minute part of the 0.9. But the same 0.1 is a very 0.01 is a very bigger part of 0.25 or 0.24. So limiting error gives least error at full scale deflection, whereas its value gives more error if the quantities that are measured are not on the full scale. So normally we are having not full scale, so limiting error gives more value. So this is just an indicator that an instrument is possessing this much error. We are having tolerance bands on the resistors in the lab, so that is also giving us a limiting error. So measured quantity would have this much error, and this will give us a limiting error. So we use such nomenclature with the error, and limiting error is always used for absolute. So these quantities are absolute. So measured value minus plus absolute error, this will give us a limiting error. Okay, so this is it for the limiting error. Now let's solve some problem with these information that we got. Let's say we are having this 0 up to 25 ampere ammeter, guaranteed accuracy of 1% on full scale deflection, that it will give us a 1% error in its full scale. The current measured by this is 10 ampere. So for 25 ampere it gives us 1% error. So if we calculate 10 ampere on it, what will be the percentage of error? So as we discussed in the previous topic, that for 10% this error would be more. So let's first calculate the value of error and then convert it that error to the percentage of tenth, in the percentage of 10. So 1% of 25 is 25 divided by 100, which is 0.25. So 1% of 25 is 0.25. Now this 0.5 is subtracted and added to this 10. So 10 plus 0.25 and 10 minus 0.25. This is the limiting error on the reading of 10 ampere. Now what we will do is that we will calculate the percentage of this 0.25 with respect to 10. So 0.25 divided by 10 multiplied by 100 would be the percentage of error on 10 amperes. So this gives us 2.5%. So an error of 1% on 25 ampere is an error of 2.5% on 10 ampere. So this is the theory of this problem. Here is another problem, and in this problem we are given the percentage of error on this 20 Henry inductance. So percentage is 20 and determine the limits of the inductance between which it is guaranteed. Okay, so the 5% has to be converted to a real Henry's or values of inductance in Henry's. So 5 to be converted 20, and this is in percentage. So percentage of 5% of 20, we have to calculate 5% of 20. So 5 is actually, sorry I have written this wrong, 5 is actually 5 divided by 100. So this is 5%. Now if you want to calculate the percentage of a quantity, let's say we are having 100 students and we want to calculate 1% of 100 students. So what percent of 100 would be 1 divided by 1% of 100. So here we are having 20 Henry and we want to calculate 5% of 20. So that turns out to be 0. This turned out to be 1. 5 by 5 is 1, so 1 Henry. So our reading would be either 20 plus 1 or 20 minus 1. So it can be either 21 or 19 Henry. So this is the theory of this example. Okay, this is just mathematical formulations, etc. These next problems, I want you people to check it and solve it. So these are left for you people. These are just same as the previous one, so just go through it. I will solve this 1.6 for you people if you want. Okay, so the measured value of a capacitance is 205.3, so this is AM, and the real value is 201.4, so this is our A. Calculate the relative error. So relative error is actually the absolute error divided by the measured value. So absolute the true value, sorry. So absolute error is AM minus A. Okay, so AM minus A turns out to be this value minus this value, which is this thing. Now divide this error divide this error by the true value. So true value is or A. So AM minus A divided by A, that turns out to be 0.0194, which is 1.94%. So this is it for this problem. Okay, the next problem is somewhat the same. So you just have to play with this equation and you can easily find the value of this true value of power. So this is it for this lecture. Let's have some discussion on the types of error as well. So there are three types of error: the gross error, systematic error, and random error. The gross error occurs when there is no mathematical treatment for an error. So if we say that an instrument is not giving us a good reading because the instrument is loading some circuit. So if we, let's say this is our circuit and we connect a voltmeter with it. So what will this voltmeter do? It has some internal resistance. So this internal resistance would be felt as a drop on these points. So the voltage might be different. So this turns out to be our gross error. So because of mistakes in observation or reading or the instrument or in the recording or calculating the measurement result. So gross error can be anything in these things, but loading effect is one of it. 2 or more readings should be taken for avoiding this error. This error can also be experienced if we use the measurement system for too long. So this part explains this thing, that if we use a resistance measurement system and the resistance heats up and gives us different values than the one we require, so this will be a gross error involvement in it. Systematic error are due to the instrument or the environment, so selecting proper instrument can avoid these error. Also the selection of a good lab or good environmental factors would also minimize such type of error. So systematic error are due to the instrument, so calibration must be done of instrument, and applying correction factor, power factor, etc. will also solve this problem. And also you should be using good environment for taking your readings, or you should have automatic compensation in the instrument. Random errors are variable errors, and these can only be minimized if the measurement is done for many times. There is no evidence of these errors, that why these errors has occurred, but sometimes the reading is wrong, and the good reading is the one which is the average of all the readings taken. Loading effect is cause of this gross error. So what is loading effect? Loading effect is the incapability of a system to faithfully measure. So a voltmeter cannot faithfully measure a high voltage if it is designed for a low voltage. Similarly, an ammeter cannot measure high currents if it is designed for low current, or it cannot even measure low current if it is measured for high current. So low current would be neglected by that ammeter. So this turns out that our chapter has been finished. So this is it for the loading effect and the instrument grading, and also the error calculation, etc. I hope you people have gotten a bigger picture of this EMI course by now. Thanks for listening.